Hello and welcome to Monday Night Calculus. My name is Curtis Brown. I'll be your host, and I am joined by the fantastic duo Steve Kokoska and Tom Dick. Super excited that these guys are here yet again to give us their wisdom in calculus and teach us some things about the calculators, which is great. I do want to just put a quick plug out here that next week we will be doing I guess, off cycle Monday Night Calculus. It won't be every other Monday. It'll be next Monday. And it'll be our last one of the season. We'll be doing one getting ready for the AP exams this year. I know that those are coming up very, very quickly. I don't have to tell any of you that. And I just want to be sure that you all know that we'll be having that link ready to go in the bulletin board blog post that we've been keeping all of the materials in this year. So I encourage you once again, to encourage your students to come and join in. I know that'll be a useful conversation, and the work that Steve and Tom have done to prepare for it, I know is going to be great. So looking very much forward to that. I'll put the link for that in the chat here shortly. And Steve and Tom, I'll let you guys go ahead and take it away. Thanks very much.
All right, thanks a million, Curtis. I'm going to try to share my screen here, see if this works. All right, how we doing? Looking good?
Taking a second, but yep, we're good.
All right, I'm going to change the view just a little bit to make this a little bit bigger. Beautiful. Okay. Indeed, Curtis, next week I'm going to talk about some common errors that have been made on the AP Calculus exam over the years. Tom knows this about me. I really don't like teaching to a test in any way, but we'll try to do a little bit of that next week and work in some concepts. And boy, there'll be a ton of questions next week for sure. So thanks, Curtis, for all the technical help and the kind words tonight, making all of this happen. Allison, it's delightful to have you back with us again tonight. I wanted to thank Mark Corrali again for publicizing Monday Night Calculus on the Facebook page. And I want to especially thank, I think it's Gerald Gillis, who had some kind words for Monday Night Calculus, Curtis, on the APSI training of the College Board. It was very nice of him.
Oh, great.
It was very, very nice. Yeah, he's been following along. I'm not sure if he's live with us tonight or if he's been looking at the videos, but he has been following along with MNC.
Fantastic.
Oh, yeah. So tonight is really a BC topic. It's about testing series. I do have lots of questions as I go through this, Curtis. I'll try to fill in a little dead air so that we can get some answers, but give me just a second here to give you a little bit of background.
Yeah, that's great.
So look, there are lots of ways to test a series for convergence or divergence. This is sort of a summary of ways to test for convergence and divergence. And the dilemma, of course, and I get asked this frequently in my class, well, look, if I consider a particular series, how do I know which test to use? Well, I kind of see this in my weird way of looking at things. Testing for convergence or divergence is a similar problem-solving technique, I believe, to integrating functions. You know, we don't teach all of these techniques of integration anymore, but Tom and I will remember going through our calculus classes and learning all of these in gory detail. And of course, one of the problems there was, well, here's a problem, and we need to integrate this function. Which technique do we use? Well, there aren't any definitive rules for that problem, and there aren't any definitive rules here for which test to apply in order to try to determine convergence or divergence. And so a little bit of my bias works its way into this, Curtis. I believe very strongly in doing lots of problems and developing good calculus vision and pattern recognition through practice. That's often a hard thing for many of my students to accept, but I think that leads to good conceptual understanding and really good problem solving. So as I go through tonight, what I'm going to think about is classifying a given series according to its form. Now, I won't always mention that, but that's sort of the goal. That's sort of in the back of my mind as I solve some of these problems. So let's start off by looking at what I call some serious series advice. How do you like that? Can you say that 3 times fast? I don't know.
I'm not going to try.
Okay. So when you're studying series with your students, one of the very first series that we all study is a p-series. Now, I haven't put in the n equal 1 to infinity here, so I'm just making this look a little less traumatic or a little less dangerous, a little easier perhaps. So this is a sum as n goes from 1 to infinity of 1 over n to the p. That's a p-series. And we learned that that converges if p is greater than 1 and diverges if p is less than or equal to 1. Now look, I'm not going to do any proofs here of that. This is sort of a summary, remember. And I'm not going to do any direct exercises involving this. Remember again that this is a summary. And this is one of the sort of patterns that I look for. Do I have a specific p-series? And you'll learn, or will learn in a minute, to have a series that kind of looks like a p-series. Now, the next most common, perhaps, series that we look at is a geometric series. It might look like a times r to the n minus 1, or a sum of a r to the n. And we know, we've learned, that this series converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. Now, sometimes, I don't like to use this phrase, but sometimes we have to use some algebraic magic to transform the given series and to make it look like a geometric series, to look like this. And we know that we have a formula for summing a geometric series. So sometimes we have to use some algebra to make it look good. So my third form that I'm going to look at here, I'm going to put a little bit of this together here. Do I have a form that's similar to a p-series or a geometric series? What do I do? Well, one thing I can do is I can use one of the comparison tests. I'm going to try to scribble just a little bit down here. I don't have too much room, Curtis, but I'm going to scribble a little bit. So here's what I mean by that. If I have a series that I want to know whether or not it converges or diverges, and let's suppose it looks something like that. 1 divided by 4 to the n minus 1. The minus 1 there is not in the exponent. It's in the denominator. Well, I can see here that that's very similar. This is a pretty straightforward example. I can see that that's very similar to something like this, 1 over 4 to the n, which is a geometric series. And so that's a tip-off that I might want to use the limit comparison test, or a comparison test anyway. So if that term is a rational function or an algebraic function involving n and involving roots, or a polynomial, I might compare it to a p-series. And I would choose p by looking at the highest power of n in the numerator and the denominator, or what I think of as, in my way of thinking, the dominant terms. Remember that these comparison tests should only be used or only apply to series with positive terms, but I could apply them to the absolute value, a sum of the absolute value of each term. So I could test for absolute convergence. So we know that if a series converges absolutely, then the series converges. Okay, thanks for putting up with that. I'm not done here. I think I've got a question coming up here in number 4. We have this nth term test. And sometimes we look at a series and we focus in on the nth term, a sub n, and we can sort of see here or prove or show very easily that the limit as n goes to infinity of a sub n is non-zero. And if that's true, we know that the series diverges. Sometimes this is called the test for divergence. So my first question for tonight, Curtis, is, what if I look at a series? I'll just write this one down, the limit, a sum from n equal 1 to infinity of a sub n. What if I look at that series and I consider the limit as n goes to infinity of a sub n, and I find out that that's equal to 0? I'm going to put a question mark there. What does that tell me about the series? So that's my first question for tonight, okay?
All right, we'll look for some people to maybe answer that question in the chat. I think that would be great.
Good. Look for some answers there, and I'll look at number 5, okay?
Ideas, floating around in the chat. I think that'd be great.
Okay. If we have a series that looks like one of these, well, that's a good possibility for the alternating series test. Here's another question. Do you know the two conditions for the alternating series test? And what happens if one of those conditions is not true? Can we draw a conclusion about the series? So what are the two conditions? This is a great review here. What are the two conditions for the alternating series test? And what if one of them doesn't hold? What does that tell us about the series, if anything? Okay. If the series involves factorials or other products, a constant raised to the nth power, we ought to consider the ratio test. And just as a reminder, this ratio, this limit here, always goes to 1 for all p series and rational and algebraic functions of n. So what happens if that ratio goes to 1? Remember that the ratio test is inconclusive. So we shouldn't use the ratio test in those particular series. I got a couple more here. I'm getting there. If a sub n is of the form b sub n raised to the nth power, that looks kind of funny, but I used a different letter in here to make this distinguishable. Then I would use the root test. Now, this test is not required on the AP exam, but I'll just remark that sometimes students do invoke it. You will never be asked to use this, but you may use it if you see that it's easy to use this in a particular problem. Remember, we will always reward correct mathematics, but you'll never see a problem where this is the only possible test. And then one of my favorites, this has been on the BC portion of the exam a couple of years here. If a sub n is equal to f of n, and we can do that improper integral fairly easy. It's kind of hard to see, Curtis, but this is italicized because I don't know what easy really means. This is the integral test, right? And here's another question, darn it. What are the hypotheses of the integral test? What has to be true before we can evaluate this improper integral, get a finite number, and conclude that the series converges? Holy Toledo, lots of questions out there. No answers yet, Curtis?
No, we haven't seen anything in the chat just so far. A lot of good questions that you've posed.
Okay.
Hypotheses, what are they? Yeah, I love it.
Okay, let's take a look.
We're not getting any responses just yet.
All right, well, let's take a look at this one. I've sort of given away some of these answers by the title of the example, but let's consider this series. The sum from n equal 1 to infinity of n plus 1 divided by 10n minus 7. Well, here's what's going through my mind in my problem-solving way of getting to this one. I see that as n increases without bound, the dominant terms there in the numerator is n, and the denominator is 10n, and I'm a little worried about that. That suggests to me that the nth term here is going to 1/10. And so that suggests to me that I ought to try the nth term test, and indeed, if you take a look at the limit, as n goes to infinity of a sub n, this limit is indeed 1/10. And I'm going to put in another question in here. Holy Toledo. I'm just going to ask, how do you get that answer? There's a lot going on or a little going on in that equal sign. I didn't put the 3 dots in there. But what's the analytic way to get that answer 1/10? I mean, we can sort of argue it as I just did. I see what the dominant terms are, and so this is going to 1/10. But how do you really do that analytically? So because the nth term does not go to 0, this series diverges by the nth term test. That's a good first one to try. Let's try this one. Limit comparison test. Well, the general term here, boy, it looks awfully complicated, but the general term is an algebraic function of n. So that suggests to me that I might want to compare this series with a given p series, and the question is which one? Well, in order to do that, we take a look at the dominant terms once again in the numerator and in the denominator, and we sort of simplify as best we can. And that gives me a tip-off as to the series that I should compare it with. So let's see, I think I did a little bit of simplification here. The dominant term in the numerator is the n to the 5th, so it's a square root of n to the 5th. The dominant term in the denominator as n increases without bound is 4n to the 5th. So I do a little bit of simplification, and I've got a 1 divided by 4n to the 5 halves. So I'm going to take a look at this limit comparison test. I'm going to look at the limit as n goes to infinity of a sub n over b sub n. I did a little bit of simplification here, Curtis, to get to here. And again, there's an awful lot going on in this equal sign, but this limit is indeed 1. Now, I might ask again, boy, how do you know that? You know, series is a difficult topic for many of our BC students. And there's a lot of nice mathematics that we bring together here into this topic. And we've got to think back here to maybe the beginning of the course, maybe the beginning of an A-B course. How do you solve some of these limits? So I'll leave that as sort of an open question. How do you solve that one? Well, since that limit is equal to 1 finite number here, this series converges by the limit comparison test. So I hope I use some good logic there when I think about my steps, my strategy that I gave you. All right, well, let's take a look at this one. And this leads to, I think, some good questions too. N e to the minus n squared. Well, okay. Boy, I don't think I can compare that to anything that I know about, like a geometric series or a P series. But this one's kind of screaming out at me. I kind of see an antiderivative in there with a substitution method. So I kind of think this might be good with an integral test. Well, before I take a look at this solution here, I have to make sure I'm giving away some of the answers here, but I have to make sure if I define my function f of x is equal to x e to the minus x squared, I have to make sure, first of all, that this is positive. Well, positive on 1 to infinity. I have to make sure that it's continuous. And Curtis, I'm going to sneak one in on you. Do you remember what the third assumption is here? What else do we need to know about this function before we can apply the integral test? Any ideas?
Off the top of my head, I do not recall that one.
It has to be.
I'm gonna pass. I'm gonna engage the audience. I'm gonna ask the audience on that one. I think I'm gonna use one of those.
Call a friend. Is that what you're doing?
Well, I think phone a friend was a different one. I'm gonna poll the audience. I'm gonna poll the audience.
Okay.
And use the audience here to help me answer this question. So you've given me 2 of the 3. I need to get
it has to be decreasing. That's okay. The third one.
Okay.
But there's more to do here, I think, Curtis. I can look at this function, and if I think about the interval 1 to infinity, certainly this function is positive on that interval. I can see that x is positive. E to the minus x squared is always positive, so the product is positive. I believe pretty easily that this function is continuous because, well, x is continuous, this exponential function is continuous, so the product is, I get that one. But I'm not so sure about decreasing. How do I know that that function is decreasing? I don't think that's obvious, at least it's not to me. So what would you do? What would you do in order to show that that function is decreasing? Well, I'm going to scribble up above here. I hope you can still see this on my screen. One thing you might look at is f of n plus 1.
Yeah.
And you might ask yourself, is that less than or equal to f of n? Is that obvious? And I'm not going to plug in the n and the n plus 1 here, but I can tell you that it is not obvious at all to me. I don't see that one. So how do you show that this is decreasing? Any ideas?
I know what I would try to do, but I don't know. I don't know, Steve. I don't
well,
know.
Thanks for being honest. Well, here's what I might do. I might take f of x, I'm sorry, I'm going to rewrite this again, and I might take a look at the derivative. Because if I can show that the derivative is negative,
hadn't thought of that. That is a good idea.
It would be decreasing. So I'm going to go through this just a little bit, if you don't mind, Curtis. I'm going to take a quick look at this. I'm going to save just a little bit of time, and I'm going to put in some 3 dots here. I would take the derivative of this by using, of course, the product rule. And I think when I did that and did a little bit of factoring, I got an e to the minus x squared times a 1 minus 2x squared. Now let's see here. I got to think about this just a little bit. This term here is always positive. That's always greater than 0. So I've got to investigate this term a little bit. And I think with a little bit of focus here, we can see that x is going to be equal to, is it plus or minus the square root of 1/2? Now we're only interested, right, from 1 to infinity. So we'll take the positive square root. And I might have to go to a sign chart and argue a little bit that, in fact, this derivative is indeed negative to the right of the square root of 1/2. So it is indeed decreasing. So there's a lot to go through here. And this would be kind of a cool, I think, free response question where students would be asked, hey, look, make sure, demonstrate that it does satisfy these conditions. So it does. Let's go to the integral test. That means we've got to take a look at this improper integral. This, again, I think Curtis has got some great review topics in it. This is an improper integral. We need to write this as a limit as b goes to infinity of this, what I call definite integral. I want to remind everyone that I see this as a 2-step process. We've got to find the antiderivative and evaluate and simplify as best we can, and then we take the limit. A common error here is that some of our students try to do arithmetic with infinity, and of course you can't do that. Sometimes in these problems on the exam, Curtis, we've seen a L'Hopital's rule embedded in the evaluation of the limit. So there's some really cool stuff here. Sorry, getting a little too excited about this problem.
It's all right.
So I finally found the limit here. It's 1 divided by 2e. That's an indication that this series does indeed converge. Another common error is to immediately think that that is the sum of the series, and it isn't. We can use a definite, we can use an improper integral to find some bounds on the sum of that series, but that is not the sum of that series. Cool. Some neat stuff in there, I think. Let's take a look at one that involves the alternating series test. And while we're here, Curtis, I frequently get asked, Jeepers, what sort of acronyms do the AP Calculus readers understand or rather accept? And, you know, we've come to accept this AST. We know MVP. We know that's the mean MVT, the mean value theorem. We accept, I think, the IVT, intermediate value theorem, probably the EVT, extreme value theorem. We probably accept IP for inflection points. Tom, can you think of any others that we might accept?
FTC.
FTC, okay, thank you. Yep.
Fundamental theorem of calculus.
Yep, we'd accept that one. I think good. Thank you, Tom. Sure. So that's a good little aside. All right, so this is certainly an alternating series, so I'm going to try this one with the alternating series test. And so the 2 things we need to show here are that the limit of the terms, the positive terms, is 0. And we also need to show that indeed the terms are decreasing. So similar to the last problem that I did, I compare b sub n plus 1 with b sub n, and Curtis, I can't tell that this expression is less than or equal to that one. I can't tell whether it's less than or equal to or not. So I will resort to this method where I will define a function to be the term of that, the positive term of that series. There's an awful lot going on in the background here, but I found the first derivative, and there it is. And let's see, can I see that that's negative? I think so. If x is greater than or equal to 1, greater than 1, I think I'm good. I see that that's going to be negative. The limit of the terms is 0. Yeah, that's pretty easy. This power, the power on n is smaller than the power on n here, the dominating term. And so, darn it, this series converges by the alternating series test. Let's take a look at the ratio test. Let's try this one. Here's one that involves a constant raised to an nth power. It also involves a factorial, a classic sort of a problem for the ratio test. I'm going to take a look at the ratio, the limit of the ratio, the absolute value of this quotient. Well, these terms are positive anyway. I'm going to do a little bit of simplification. I'm sorry, Curtis, go ahead.
Excuse me, Steve. You know, I just caught something, and I'm sorry I didn't notice this before, but on your previous example,
yes,
everything you said was fine, but it just occurred to me that I think that series has to start with an index of n equal 2 instead.
Indeed it does, yes. Yeah, indeed it does. Thanks.
Sure.
So here, I think, Curtis, in this line, this first line, I did a little bit of simplification here, division of fractions. And then let's see, I think I can cancel out all but one of the three. So 3 to the n's go. And let's see, there's an n factorial that goes. I'm left with n plus 1, and that limit is 0. And so that series is absolutely convergent and therefore convergent. That's a nice standard sort of a problem, which somehow might be worked into, I think, a multiple choice problem, which I've got coming up, believe it or not. All right, how about this one? Let's see, 1 divided by 3 plus 5 to the n. Well, as I look at that, I quickly think about, well, it seems like it's related to this geometric series. So I'm going to use a comparison test. And let's see, for me, this comparison, I think, is pretty easy to see. And the reason is because for any value of n, that denominator on the right-hand side is larger. Did I do that correctly? So this series converges because I can compare it to a geometric series.
Mm-hmm.
All right, I've got one question for the crowd here, Curtis. I don't know if I'm going to give an answer to this one or not, but this is kind of a cool multiple choice question, so one that you might see on the exam, I think.
Say, Steve?
Yes.
Sorry. So I think that inequality is
backwards. Yeah. Yeah.
But it's interesting what the fix would be, I think.
Yeah. How would you do that?
Are you asking me?
Sure.
Well, I think I would compare 1 over 3 plus 5 to the n to 1 over 5 plus 5.
I think that's a great idea.
Is
so I think what I would do is something like this.
Or maybe 5 times 5 to the n. That
would be even better.
Yeah, that's the one to do.
I think that's the better one. Yep. All right, how about this one, Curtis? I don't have a solution here written down, but I think this is a good one. Which of these series converge? Yikes. I think with everything that we've talked about this evening, with all of the strategies, the advice that I've given you, I think you can figure this one out. And maybe we'll leave that as an open question.
I'm glad the "you" was not necessarily directed at me, but I know that you've given them some great tools here.
Any guesses?
So.
Or do you see any that diverge quickly?
You're asking me?
Well, anyone.
Okay, we'll let the audience answer that question. Maybe put some in there that maybe are definitely not the answer.
Okay.
So we'll ask that perhaps,
right.
And then we can follow up with, okay, so which one might actually?
Are there any that diverge quickly? For sure.
Yeah.
Okay.
Sure.
All right. We had some great exercises here, Curtis, to go along with series. I'm going to take a look at a couple of these quickly, and then I'll hand it over to Tom. So our first one was determine which of these series, whether the series converges or diverges, and explain your reasoning. So I'm going to assume that our participants have looked at these problems and handed in their homework for us to be graded through you. So I won't look at these in gory detail. In this first one, I think in 1A, I think that's a great candidate for the ratio test. This is, of course, very similar to one that I just did a moment or two ago. And I think after all of the simplification, we get this limit is 0. And so this series is absolutely convergent and therefore convergent. In part B, as I look at that one, here's how I'm thinking about that and solving that in my mind. I see the dominant term in the numerator is n. The dominant term in the denominator is 2n, and so I'm a little worried about where these terms go, what happens to them as n increases without bound. And so I took a look at this limit. There's a little bit going on here in that equal sign. I divided both the numerator and the denominator by the highest power of n in the denominator. And then I think it's a little bit easier to see that this limit is indeed 1/2, which is not 0. And so that series diverges by the nth term test, or what some call the test for divergence. This one is pretty easy, and I did this one in a long-winded way, but we can look at that and see pretty clearly that that is very similar to a p-series, so we could do some comparison tests there. But you could also do this one with the integral test. It's kind of a nice problem to do with the integral test. You've got to convince me that it is indeed continuous, positive, and decreasing on that interval. Again, we have to evaluate this improper integral. So that's some nice BC mathematics calculus going on there. I like that one. So the integral is convergent, and therefore this series does indeed converge by the integral test. And D was kind of a nice one too. This is actually an alternating series. I'm going to let, in my notation, I'm going to let b sub n equal 1 divided by the square root of n. And let's see, did I get that inequality right? I think I did, because n plus 1 is bigger than n, so that denominator is bigger, so the fraction is smaller. So yeah, that inequality is correct. The limit as n goes to infinity of b sub n is 0. So here are the two conditions for the alternating series test, and therefore that series converges by the AST test. Tom, you're going to have to help me on this one. I'm not sure if I remember this one. Do we know the sum of this series? Is that one that we know?
Oh, I don't know.
I'll let you think about that one. I'm not sure if that's one we know or not. Here's another sneaky one. So it kind of looks like an alternating series, but be careful here. I don't know if they would try to sneak one by you like this on the exam, but that 2n means, darn it, that power is always going to be even, which means this really isn't an alternating series. It's really just simplifies to a p-series with p equal to 1/2, and so therefore this one easily diverges. And by the way, you know, when students are testing, say, endpoints in a Taylor series problem, and they plug in one of the endpoints and they can see here that they have a p-series that converges or diverges, they really don't need to do anything else to prove that. They can simply say, look, this is a divergent p-series. You know, you can add a little bit more in by telling us, you know, p is equal to 5. So this is a convergent p-series. But they don't have to prove anything there generally. And finally, my last one down at the bottom, a good candidate for the ratio test. Let's see if I did everything correctly. I did a little bit of simplifying of that ratio. And by the way, this is another tip for the exam. I don't think I'm going to talk about this one next week, but this is another tip for the exam. You know, if you're using the ratio test, it always seems to me a little bit easier to take a look at this quotient, this ratio, the absolute value of that, and simplify that as much as possible before you even consider the limit. So in my mind, this is sort of a two-step process here. I'm going to look at this ratio, this quotient. I'm going to simplify as much as possible. And now in my second step, I'm going to take a look at the limit. And indeed, this limit is 1/2. This expression here inside the parentheses goes to 1. You can kind of see that by arguing, because the dominant term in the numerator and the denominator is n. So this is getting closer and closer to 1 inside the parentheses, therefore going to 1 squared, or 1. So this series converges by the ratio test. Well, I think those are some great problems in there, Stuart, and I think Tom's got some excellent technology here to show you with series. So I'm going to stop sharing. I'm going to hand it over to him. And there you go, Tom.
All right. So I'm going to try to share my TI-Nspire. And can you see that screen all right?
Yes, sir.
Looks good.
Okay.
Looks great.
Let me, wanted to address a couple more of the exercises that Steve started us out with the several series. And this was our second one. And we kind of picked this one because it really illustrated why that, what I call the monotonic condition on the alternating series test is so important. And so it's really kind of this arbitrarily drawn up series to illustrate what can go wrong if you don't check for that. So that number 2 there is for n equals 1, 2, and 3. We're going to have the even index terms, that'd be the a sub 2n, are really going to be the terms in the harmonic series. And the odd index term, that'd be the a sub 2n minus 1, they're going to be the negatives of the terms in a geometric series. Okay. Now, if you actually write that out, it's going to look like, so your first term is negative. If you look at the first, third, fifth, you'll notice that those are the negatives of a half, a fourth, an eighth, a 16th, and so on. While the other terms, we've kind of perfectly shuffled the harmonic series with the negative of a geometric series. So it's definitely alternating. And the terms are going to 0 because the odd terms are 1 over, negative powers of 1/2. So those are going to 0. Separately, the even index terms, they're the harmonic series. Those terms go to 0. So all the terms are going to 0. But you notice that it's kind of jumping around a bit. We go from, if you look at the absolute values of the terms, we go from negative 1/2 up to 1, then down to negative 1/4. Absolute value would be a 1/4, then back up to a 1/2. And that's violating that condition for the alternating series. So we can't really use the alternating series test here. And in fact, if we think about it, we would have to conclude that that series actually does diverge because the positive terms in it are overwhelming the negative terms. The negative terms are going to sum up and converge to the negative of the sum of a geometric series, while the harmonic terms are going to diverge on us, and that just is a complete washes out any effect there. So that series is going to diverge. Even though it's tempting, students, I think, are tempting that they're just looking for terms go to 0 and alternating. Those are the two conditions that really stick out in their mind. But that kind of monotonically decreasing in absolute value size is really important.
That's a fascinating one.
Yeah. Now, you can reel me in here, Steve, if this was a little far afield, but we've really been concentrating tonight on series of constants, but kind of in that general topic, people look at Taylor series and Taylor polynomials. And I did want to put in a plug for Steve really emphasized the one of the important tests is the ratio tests. And I would kind of double underline it. Steve gave us, one of the hints that ratio tests might be important is if you see a factorial in your terms. Well, if you're looking at Taylor series, they almost always have factorials involved by definition. And so the ratio test is really helpful for determining the interval or radius of convergence. So ratio test is really going to be a super important one. This number, go ahead.
No, agreed. Yeah, agreed.
So this number 3 here was just something I was curious about is what if you tried to find a Taylor polynomial approximation to a function that was already a polynomial? So the example here is a cubic, f of x equals 2x cubed minus 5x squared plus 7x minus 6. And we're looking at a couple of different second degree Taylor polynomials. So you could find one that's expanded around x equals 0 and find a different one that's expanded around, say, x equal 2. How would these look if you graph them? Well, let's go ahead and cut to the chase. There's a picture of them. And if we think about it, it really makes a lot of sense that, I mean, a parabola is not going to look anything like a cubic. And so the good fit that the parabola has will have to be really local. And so the one where we expanded around 0, well, that parabola really fits that cubic pretty well near 0. And the one where we expanded around 2, well, that parabola fits pretty well around x equal 2. But in general, you would say globally, neither one's going to be a good fit because parabolas just doesn't look the same as a cubic. All right. Now, you could look at this cubic and think, well, that's kind of looking like a Taylor polynomial that's expanded around 0, even though we usually would put the constant term first and then go up in powers. But that's just kind of rewriting terms in a different order. Question is, what if you found, let me skip down here a little bit here. And sorry for my fumbling around. The question is, what if you did a third degree Taylor polynomial for that cubic polynomial, except you did it around some other point?
Mm-hmm.
So I've got a cubic, looks like it's expanded around 0. What if I did the cubic Taylor for it around x equal 2? Well, let's take a look at those two graphs. You can't tell the difference. They're exact match. And so, yeah, so if we match up the, it doesn't matter what point we expand around, we'll get a perfect match on Taylor polynomial if we actually match the degree of the polynomial that we're looking for. So. And another part of this exercise was to actually look at the Lagrange error to make some sense out of that. So I wanted to turn to some tech tips, and one of the things I'm going to look at is just out of curiosity, I'm on a TI-Nspire. I'm going to turn to the TI-84 here real quickly, but I went ahead and did a P-series using a computer algebra system on the TI-Nspire. And for k equals 1 to infinity, 1 over k to the p, well, if p is equal to 1, notice I've put the power p on a slider. So this is actually the harmonic series. And the computer algebra system has just spit that back, but we know that the harmonic series diverges. Now we know that once we make that power bigger than 1, this thing should converge. So I'm going to go ahead and ratchet up the power to p equal 2. Now that's, I think, a big surprise to a lot of people. Okay. This is actually returning the exact sum of that series. It's what the partial sums converge to. And it's interesting that pi would pop out of this. It's even a power of pi squared over 6. How bizarre.
Yeah.
Now I'm going to crank this up to p equals 3. Oh, now we know that this, by the p-series, and by the way, the p-series, they're based on the integral test. Okay, so we know this converges, but the computer algebra system has no clue what this is. And I point out this is an open question. We don't know exactly what the sum of the reciprocals of the cubes, what that series converges to. But if we crank this up to 4, oh my gosh, pi shows up again, but this time it's pi to the 4th over 90. P equals 5, open question, no one knows. P equals 6, and you're probably seeing, Patty, you could guess that if I crank this up to p equals 8, maybe pi to the 8th would show up. You'd be right. So it's really wild what's going on there. So, now, just for grins, Steve.
Yes, sir.
While you were talking, I tried this one out on a computer algebra system. This was that alternating series that you were looking at with had square root of k.
Oh, yes.
Denominator.
Yes.
And I asked the computer algebra system, and I'm not saying it's an open question, but this computer algebra system didn't know what it was.
Mm-hmm.
But notice what it did do. It wrote the -1 to the k in kind of an interesting way. It rewrote it as cosine times k times pi.
Yeah.
And let's see, the odd multiples, for k being an odd integer, an odd multiple of pi, cosine would be -1.
Yeah.
And if k is even, cosine of k pi would be +1. So that's kind of a clever way, alternative way to write alternating for even and odd k values.
Yeah.
So,
yeah, that is an interesting method by which to get that alternating plus and -1.
right. Okay. Well, I'm going to shift over to the 84, gents, and let's see. I think I might, since I did that application, I'm going to do a quick stop share, but then share again and pick the 84 up, and I'll let you tell me if I've succeeded in getting a TI-84.
Looks good.
Okay. Yep. So here's the TI-84, and just want to talk about exploring series. One of the points I make with my students when they ask about convergence tests is, I point out there's really not that many series that we know the exact sum for. Mm-hmm. Geometric series is one of the very few. And we saw that somebody has figured out a few of these P-series. The P-series are kind of wild. They have those powers of pi in them. For the even powers, but that's a big open questions. But if you know that a series converges, then it actually kind of tells you it might be worth your time trying to approximate it. I don't want to waste my time trying to approximate a divergent series. That's just a complete waste of time. And so this convergence question is really a meaningful one. So I wanted to look at what tools do we have on like the TI-84, purely numeric for investigating series. And there's a type of plot that I think is really helpful here. And it's the sequence plotter, because series really are sequences of sums. So let's take a look at that. So I'm going to go to the y equals menu. And normally we would see the y equals, y1, y2, and so forth. I'm going to bring up a different kind of plot, and that's the sequence plotter. So to do that, I'm going to go to the modes. And you'll notice down here on the 5th line, those are where our plot modes are: function, parametric, polar, which we used, I think, last week, yeah, or a couple of weeks ago, and then sequence. So let's go ahead and pull up the sequence plotter. And while I'm at it, for sequences, instead of a thick curve being drawn that's continuous, I'm going to use dot thin. So it's going to put a thin dot for each sum, for each integer value. Okay, so that's why we'll set up the plot. Now, when I return to y equals, I'm going to see a really different setup here. Okay. So now I see a sequence, and it has a new independent variables, this kind of italic n here. By the way, your independent variable key now is dedicated to that n value. So what I'm going to do is actually put in the sum for that 1 over k squared thing that we looked at a little while ago, that sums to pi squared over 6. So let me go to the math menu, and let me scroll down to summation. Okay. And I'm going to have my summation. I'll use k for my index variable. I'm going to start at 1, and we'll go up to n. Okay, so n will be where my sum tops out at the index value. So I'm going to use that independent variable key. There's that script n. And then I'm going to put in 1 over k squared, which is my index. Okay, so my first term in my sequence would be the sum from 1 to 1, 1 over k squared. The second term, or the second sum, would be the sum from 1 to 2, 1 over k squared. So each term in this sequence is actually a sum. All right, let's take a look at what the plot might look like here. I'd like to see what the first 100 partial sums look like. So I'm going to go to the window here. My minimum is minimum n is 1. Let me set my maximum n at 100. We'll start at 1. We'll step by 1. And let's see, let x min, I'll make it -5 just to give us a little bit of space for the axes. And I'll just go up to 100 because that's where we'll stop. And then we've got our standard scaling here. So let's go ahead and graph this, take a look at what it looks like. And so we can see that each one of those dots that you see plotted is itself a sum. And you see this, it's looking like a curve, but it looks like it's very flat. Okay. In fact, let me go ahead and change the window a little bit here. If I can, maybe it's still plotting. Let me change the window, the Y, get a little bit. Let's have the Y min be 0, Y max be 2. So we can see that it's certainly looking like this series is converging. But this is only graphical evidence. I just want to emphasize this is just us kind of exploring what this is doing. Now remember, this was supposed to be converging to this kind of weird value of pi squared over 6. I wonder where pi squared over 6 is in this picture. So what I'm going to do is I'm going to quit the graph and pull up, when you're in a different graphing mode than your y equals, you might want to try this. Okay, I'm going to go to the draw menu. And you can draw, in this case, we could draw a horizontal line. So I'm going to go to number 3 there, horizontal, and I'm actually going to put in pi squared over 6. And there's pi squared. Now, so that should draw the horizontal line y equals pi squared over 6. Let's see what it looks like. Ah, nice. We can see how that our sequence of partial sums is approaching that horizontal asymptote. So that's kind of cool.
Tom, does that draw menu work for any of the functions? Like if we were in a polar plot, could we go back to the home screen and add a horizontal or a vertical line?
Absolutely. Yeah. In fact, you can also, one of the options in that draw menu that's particularly nice is draw F. So you could draw any function plot, even if you were in a different mode, like polar or parametric, you could superimpose a function plot on top of it.
So you could draw a tangent line to the curve at a point?
Exactly, yeah. That's where I use it the most. I'll use draw F to do tangent lines to polar or parametric curves.
Gotcha. Okay.
So it's a very nice feature.
Mm-hmm.
Yeah. So one of the things that I wanted to show is a way that you can help your calculator out is, did you notice how slow this was graphing? That's because if you think about it, we were asking for every single value of n, we're asking it to do a sum. And it's doing those sums by scratch. So when it gets up to n equals 98, it's summing from 1 through 98. Then when it gets to 99, it starts over again and sums from 1 to 99. So that's not really smart. So I'm going to change my approach to how to sum these sequences. I'm going to do sequence n plus 1. And this is a way to kind of recursively define your sequence values. And the way I'm going to do this is I'm going to think of it, say, well, for each term in my sequence, what I'm doing is adding 1, whatever the current value of n plus 1 is, I'm adding 1 over n plus 1 squared to my previous sum. So what I'm going to do is, let me delete this. So let me get a lowercase u. And I'll say, okay, u of n plus 1 is u of n plus 1 over n plus 1 quantity squared. And I do need to tell it where to start. So that's where you see this u1 equals 1. So the first term is 1, and now it's just going to build sequentially there. So now I'm going to go back to my window. I want to plot the first 1,000 sums. Now this would take a day and a half if I made it do each of those sums separately. Should plot pretty quickly. Let's take a look. Oh, sorry about that. You can see it's graphing pretty fast. And that's because I'm really only making it add one term to the next, to the previous partial sum, rather than have it do this enormous amount of calculation. So we can really give the calculator a hand and kind of use our math smarts to make it work smarter too. So.
I like that, Tom.
That's cool.
You know, that's a good tech.
Cool.
That's a really nice tech tip.
Yeah, and I think we're probably pretty close to out of time. So
yeah, I think we're right on time there. So Tom, Steve, thank you a whole bunch for this. And while I'm at it, I just want to thank you for this whole series. This has been a real blast working with the two of you this year. Being able to do a little bit. I apologize that I haven't learned all the calculus. It's been a little while since I've taken some of this, and so early on maybe I was helpful, but in the recent ones I think I've missed some things, but that's okay. I really appreciate
it. Been a blast for us.
Yeah, sure has. Sure.
And look forward to doing this again. But next week we'll be doing, just as a quick reminder, next week we will be doing a test prep, sort of a focus on the AP calculus exam. Steve's going to be looking at some common errors, and Tom, you're going to be looking at some common strategies for the calculator. Is that correct?
Yeah, some pitfalls to watch out for, as well as some good just good practices for making the most efficient use out of your calculator.
Okay, well, that's going to be really, really useful. So I would highly encourage you to go ahead and reach out to your students, make sure that they're logged in next week at 7 o'clock, ready to go. And I guess that's our time to sign off here tonight.
Thanks, Curtis.
Guys, we'll see you next week.
Okay, deal.